colloquium. Our speaker for today is Dr. Anshu2. He recently completed his PhD from Cornell and is now an assistant professor with us at Rice. And so just before the talk, I asked Anshu, how should I introduce you? And he said, well, you can say I'm one who keeps transitioning between a graduate student and a faculty. So let's see what he is today, a graduate student or a faculty.
Thank you. I don't know. This is the work that I started when I was a graduate student, but almost completed when I am a faculty. So you will see both of them. So I'll talk about a scenario and how machine learning applied on that scale. What are the challenges, and then we'll show you some solution and something new. So that's what the plan is. So let's look at a concrete problem. Like this is one of the classical online setting problems where you are given a query. So you are in an online environment, a user types a query, and then there is some context. For example, we know where his location is, for example, from Rice, and this is typical what Google and search industry is interested in, is showing you an ad which you are most likely to pick. And so we want to find, or we want to predict this quantity, which is the probability that you will click on an ad given user and context, and whichever ad has the highest probability, that is what I will show, and that will make money. In fact, this is $230 billion industry that was estimated this year. And so if you pull out some data, like how the data set looks like, so this is the example data if you pull out from the Kaggle competition, but you will see that you are given some user ID, you are given some query keywords, you are not given the exact keywords, you are given the hashed, because after that Netflix disaster, people know that if I know all the queries, and if I partially know someone's query, then I can just match and see who this guy is. So you are given all these information are hashed except this timestamp. So you can maybe you get what the ad URL is, hashed again, what ad keywords are, and this is pretty much the data set, and you are asked whether he will click on this ad or not, or what is the probability that this user will click on this ad. And if you think the data set is IID, and if you just run your machine learning algorithm, you are not getting anywhere, because this is very important. There is correlation in time, and that is what we'll see how to exploit. And roughly to give you the scale of the problem, as I already mentioned, it is a $230 billion industry. There are billions of users and more than tens of millions of ads. And if I take into account the combinations, it simply blows up. And what I mean by combination, it's like the context. For example, is he clicking from Rice University? Is it a month of Thanksgiving? Or is it a holiday? It could be anything interesting. And just if I look at the ad cross query combination, it is already more than 10 to the power 10 plus. Now with this giant scale, you have to make a very fast decision, because he's typing a query, and if you are showing him some ad, if you are taking a lot of time, he will just vanish, and this will be of no use. And a typical response time requirement is 50 milliseconds. And on the top of this, you have to update models on the fly as clicks and non-clicks are observed. So imagine this online environment, and there are lots and lots of users who are simultaneously interacting with your online browser. They are clicking on some links and not, and you have to keep updating your models on the fly. There are bursty patterns, and it needs very frequent retraining. So if you have built a model, then patterns change quickly over time, something like a stock market, and so you have to retrain or understand what the current pattern is going on quickly. So this is a typical set of challenge, and as I mentioned, that this timestamp is very important. For example, if you just run whatever boosted trees or SVM on the Kaggle competition, you will probably be doing as good as the baseline model which the competitioner themselves provide, that yeah, we run an SVM and this is the benchmark that we achieve. You will achieve the same if you are not using that time information. So that temporal information is very critical. And I don't have to justify why, because for example, everybody will agree if I say that the number of clicks on some ad in the past hour or past month is a good indicator of whether it will be clicked again. And so I'm looking in the past and maybe some amount of time. And again, this is just one example. You probably want to look at a lot of combination, whether this user has clicked on some ad or he has done some other activity online, and you have to create features of that. There are short-term bursts. For example, a user won a lottery. So his behavior is going to be very different, and it's going to be short term. So you want to understand that, and also there are long term patterns. Like you cannot ignore everything in the past, because that gives some information about what the mean intrinsic characteristic of a user is, or for example a product is. So this is the information that we want to like capitalize on. And if you're wondering that ad click is just one example, actually it's almost all of the online environment is like this. For example, if you look at fraud detection, it has very similar characteristics. Like you're doing an online credit card transaction, and the bank has to approve or decline depending on whether they believe that you will return that you are capable of returning that much amount back or not. And again, there are temporary trends in the transaction. For example, how many transactions he has done in the past, what is the amount, is there a fraudulent activity, how does the fraudulent activity look like? It's similar. And again, there are same kind of challenges in stock market prediction, that you are trying to track some indicator X and maybe joint with some stock X and Y, and these patterns change over time. So the fundamental problem that we are dealing with is, how can we reasonably identify these temporal patterns? First of all, we need to identify what those combinations which are interesting and relevant for the current task is, and how to make a machine learning algorithm aware of it. And of course, it's not just on a toy example, it's on a humongous scale, where even the add cross query combination is more than tens of billions. So that's a typical challenge which industry people are facing, and in fact a lot of people are working on it. And if you look at talks from Google, Yahoo, Microsoft, most of them talk about almost similar sort of stuff. And so we'll look into what things are going on. So what is common in this, again, like it's a machine learning environment, so if you're thinking that, okay, the usual pipeline will be find some good features, run a machine learning algorithm, you're almost right. But the thing is, you cannot do more than, like, a linear is also not doable most of the time. Quadratic, forget about it. So you have to build features which are very cheap to compute and useful. And what is being almost standard in this industry is what is called count-based features. So what is a count-based features? So suppose I'm looking at a category. Maybe it's just the pin code of, for example, it's the location, which is the location Rice University or not? And what I'm keeping track of is the number of clicks from that location and the number of non-clicks for maybe some, or maybe in general, number of clicks and non-clicks. Maybe people at Rice like to click a lot as compared to outside the Rice. So this could be one table, and of course there are humongous numbers of tables that you simultaneously keep track of. You are keeping track of the count of clicks and the count of non-clicks. So this is in some in a naive-based sense. This is you are computing the odds of whether this indicator is present and what is the odds that he is likely to click. And in technical terms, these are called naive-based type features. So there are many such tables because you don't know which one of them are interesting. And when computing the feature vector, you take the query, take the ad, take whatever context it is, and see which one of these you hit. For example, is the person from Rice University? Okay, so you hit this guy, and so there will be a corresponding location in the feature vector where you will aggregate this information, maybe take the ratio or take the log odds and generate a feature vector. So this is going to be a very sparse feature vector where the non-zeros will indicate that there is some indicator in the query ad combination, and it will also indicate what in the past the clicks and the non-clicks look like. Of course, I haven't gone yet into the temporal aspect of it, but this is just aggregating everything till time t. Ideally, you want to know what was happened in past hour or past minute. You want to get more information because there may be a temporal burst. But let's, for the time being, look at what count-based features are. So it's a very sparse feature vector representation, and once you get a feature vector representation, you can use any favorite machine learning algorithm like SVM, neural net. Boosted trees might be a problem because this is something like a trillion dimension or billion dimensions feature. So I mean, I always used to wonder why like industry care about a trillion dimension feature. What kind of information is present there? So it's either bag of words or these kind of features. So it's the combinations. And people keep this because it's helpful. It gives some boost. So this is this kind of algorithm is rediscovered many times by practitioners. Here are a couple of some references, and it's almost standard in online industry. All right, so that's what you do, and why Why people want to do this? Because it's extremely scalable. You know, I mean, a classical example of map reduce when it is taught in class, you tell you how to aggregate words. And here we are just aggregating, so it's a classical map reduce operation. It can be massively parallelized because you are storing different tables, so every machine is responsible for counting few set of features, and you can extract this massively in parallel. It's the state of the art, it works really well. Counting can be done on the streams. I will touch on this little later, what I mean by streams. You only see the updates. And this is there are only few things that you can do on streams. You require less frequent training. Why? Because remember here, if I train a model on this feature vector, then if suppose there is some new trend that is coming up, either I have to retrain, but remember these counts are getting updated. So if this feature gets really lot of importance, then that will, that will show up in the feature vector itself. So this requires actually less frequent retraining. And if you find that there has been some malicious data that you have used on, you simply subtract because you are counting. So it's really, really simple and works well. But there are still some challenges which we'll look at it, because I was talking that the combinations are humongous. So I cannot keep all the tables. So I have to actually decide which one table to build on. And again, this changing pattern over time, I have to do something about this. Yeah, and feel free to ask questions, or you have any any doubts. So one thing good about this world is that most of the things follow power law. So what is power law? I just rotated this power law usual distribution picture. So this is usually your features, and this is importance. So what happens is there are few features which are most important that will give you a lot of benefit, and then other features will go in the tails and give you marginal returns. And so ideally, if I have given limited budget, like I cannot store all the combinations, I would like to identify, so if I have given a budget of 1,000 features, I would like to start from here and go down in the 1,000, this thing, to get a maximum benefit. Of course, I don't know what the ordering of these features are, because if I would have known them, then this problem would have been solved. So the classical problem is there are too many features, some of them are important, how do I identify them? And this may very well sound like a feature selection problem, right? Like, yeah, we are doing feature selection. We have to be slightly careful about it because the number of feature matters in practice. So the tails are very heavy. You want to know this ordering, but it's known that the more feature you use, the better you become. So this is a study which was published in 2001 by Microsoft Research, and the conclusion of this study was that in the conclusion paragraph they have written that people tried comparing models. Instead, we hope that people now push more effort in collecting more data. So what this plot is showing is that there is a very simple memory-based and Winnow algorithm and naive bias, and there is a little complicated algorithm which is a perceptron. So this is linear, it has some dependency, and this does not even have any dependency. And most of the model perform as good as anybody else. The other thing here is that as you keep increasing the number of features, the accuracy keeps climbing, and it's on the log scale. So this also indicates power law, because you need logarithmic many improvement to get something like a linear improvement here. Now plots actually tells you a lot. Looking at this plot, I can tell you that if you are trying to do a feature selection, saying that, okay, let me try to find best 1 million word, and maybe everything is in that 1 million word, that's not going to happen. You can almost tell this from this plot. Because if that would have been the case, then you would see kinks. Because if their feature selection would have mattered, the time you would have selected that feature, you would see a big jump. But that does not happen.
So you assume the training data is always adequate, right? When you have more and more features, you're going to have the person having to manage it.
Right. Oh, so the training, so we are assuming that the data is enormous. Like we have lots of data. N is typically very big. And we have this is on a test set, a fixed test set, which is reasonably big. And then we start adding more and more dimension, more and more feature, more and more combinations. And the more you add, the better you become on the test set. So that actually shows that, well, and that is what one of the argument of this paper was, that you should put more effort in actually collecting and annotating data rather than comparing different models. But it was a nice study, and this is what is typically observed in online environment. That the more features you use, and this also tells that this power law is actually very heavy tail. So the more you go down, the better you become. But again, you want, like, you cannot keep all of them. So you still want to be smart enough and start from here. So that's the challenge. So we are given how to identify significant indicators without having to count all of them. So the problem is I cannot even keep counters for all the features because they are huge. But without counting every of them, I want to know which one are heavy or which one has a lot of counts or which has significant effect. Now this is a classical what is called a streaming setting, and the way this is formalized is what is known as the turnstile model. So what a turnstile model says is that assume we have a very long vector of dimension d that we cannot even materialize. So d here is actually the number of combinations that you want to keep track of. So you want to count, and what you are seeing is only increments to its coordinate. So at time t, an increment comes and says that okay, coordinate I is incremented by 10. And that is all you see. And you keep seeing it throughout the time, and in the end, you want to find S, where S is some number of heaviest element that you can afford, that is your features, S heaviest coordinate using the space which is much less than D. So you cannot enumerate the vector, you have a short memory buffer, and you want to find what are the heaviest element, and you only see the counts, you don't see the full counts, you only see the updates. Almost seems hopeless.
What do you mean by materialize?
So materialize as in like you just think about it in the memory, like in your mind, but you cannot have that much memory for it.
Okay.
So you cannot keep you cannot allocate that much in the memory.
Can't we just use this database? Just use hard disk and say even bigger that your
So the hard disk would be like, so these are streaming updates, right? So assume that you are trying to store everything that occurred in place. So let's say I'm trying to, just add cross query is 10 to the power 10. If you want to cross it with say number of combination, number of time, you are already going in 10 to the power 20 or something. Now if you want to store it in the hard drive, then you want to read it back, and you have to do it on the fly.
Can you give a concept like how big is really big, like billions of like tens?
Oh, so the number of users is billions,
Right.
the number of ad is tens of millions, and the context is like, it depends on what you can afford. So context could be the pin code of the location, it could be that there is a keyword called XYZ or the keyword called beer in the query or the keyword called
So
anything.
basically, D is so large that there's no runnable computer can store it in memory.
Right. It's like the classical streaming or the turnstile model. It's like you can think of network traffic. So network traffic also has the similar phenomena. And it seems hopeless, right? But I don't know, this was actually said, I'm sure this was said in a very different context. This was by a philosopher, but this is what we are going to do, and it actually works. So here is what you do. You do the dumb thing. Okay, so I cannot allocate that much memory, so let's allocate whatever I can, and then randomly throw items into it, and this will work. And there are actually many citations that shows that this works. And if you are wondering that this is such a simple and dumb algorithm, then it won the Test of the Time award recently. And it has again very good connections to compressed sensing, which is like considered a very sophisticated field. So why it works? So remember we want to count heavy elements, and in a stream, like most of it is noise, and there are few heavy elements. Few as in still millions and billions, but much less than what the total number of things are. And that's what the hope is. So here is what, so if you see, I'm throwing an item I into some bin. If this bin, so throwing it randomly. So if this bin does not receive any other item, then I'm counting item I exactly. Because I'm accumulating all the aggregates in one bin, and that bin is the exact estimate of what its count is. Now, problem is because there are too many items, there will be collisions. So let's see what happens when there is a collision. So when there is a collision, this scenario does not bother us. Why? Because there is a heavy element and there is an irrelevant element. So if I want to estimate, so if I just return the estimate of this heavy element as this counter, I am not incorporating much error. It's still good. This is irrelevant, we don't care about it because these are anyway two very small quantities. This counter is very much small, we can ignore it. This is the unlucky thing. this might happen is that when two heavy elements goes in the one bucket, there are two good things that we have relatively few pairs of heavy elements. So this is slightly unlikely, but still this can happen. And so we can minimum. And by the way, this is like, this is survival of fittest, right? When two people mess with each other, the fitter one survive with less distortion. That's simple, right? So just randomly throw things into it and it works. That's the reason why. And you can do you can be a little bit more smarter, and that is actually this algorithm which is known as count and sketch. So remember, we always overestimate. Either you will be exact or you will always overestimate. And you are unlucky if two heavy elements collide, and then you will overestimate by a lot. But if you repeat this independently d times, where d is some number that you can choose, and take the minimum of all overestimates, then unless you are really, really unlucky, in which all the d times your element has collided with another heavy element, unless that is the case, this estimate will work. And that is what is the theory behind what is called count and sketch. You can show that you get a very good estimator with very high probability. And the way it works is you have d repetitions of what I showed here. So this is just one hash function. Here you have d independent hash functions. You put them in the counter, and when you want to estimate what is the estimate of counter I, you take this, take this, take this, take this, take this, and return the minimum of the estimate. And this is very good, because if all of them has like a heavy element colliding with this, that is very rare, and so for most of the items you will do very good. So that's classical count and sketch. And there is in fact almost equivalence with what is known as compress sensing. So if you are aware about this field, which is like very popular, remember our setting was, the streaming setting was, we have a very long vector, we only see increments, and then we want to find S heavy coordinate using this much space. The compress sensing problem is, we have again a very long vector, and we want to find S heavier coordinates in much less measurements, and these are linear measurements. And this is like a classical compress sensing problem, which is like, it's a very big field in statistics and even electrical engineering. And what is recently found is that hashing is equivalent to a random sparse matrix multiplication. You can show that. So the state of the art technique for compress sensing is you take a random Gaussian measurement. So this A matrix is simply your random Gaussian measurements, and it works. And what you can show is that when you are computing hashing of V, you are actually computing a random sparse matrix measurement, and you can show that it's almost near optimal. So there is a very strong equivalence between compress sensing and these streaming kind of algorithms. So alright, so far we know how to, okay.
What is measurement exactly?
So measurement is you want to, so measurement is like you can just store numbers. So you store few numbers and you should be able to reconstruct the whole vector. And the number should be a linear measurement. This comes from some hardware requirement, but because what you see is you apply a lot of filters, and filters are linear. So what you get is an output of that filter on the signal.
Linear in what?
So linear is a matrix times the vector v. So that's linear. Okay. So this is roughly known that we are given how to count on streams, that we cannot keep track of all the items, but we can still reasonably estimate heavier items. So now let's see how we want to incorporate the temporal features. So the temporal features would be the same indicators that you want to keep track of, plus you want to smear it over time. So this t is going to be very big. You don't want to be big O of t. So to get logarithmic in t, what people do is they keep increasing size window. So this is your current time instance t, then you look at what happened in previous time instance, and maybe this interval, this interval, this interval, and you keep track of all those indicators in this log t intervals. So that is, so the reason why you want to be more accurate, because recent trends are more important than older trends, but then this is what is usually people deploy in practice is like, okay, let's keep a small sketch of what happened in time. So this gives you roughly enough information of what the variations are. And then again, like, so you do count based algorithm on this, and it works. there is this recent requirement of what is known as time adaptability. So it's known that recent patterns are a lot more informative. For example, in fraud detection, a person's recent credit score variation is a much stronger indicator than, for example, what was his credit score in past. And we need to quickly find what are emerging heavy hitters. So what are emerging heavy counts that we need to identify before it's too late. For example, the nature is very bursty, and if some fraud is happening, we should know it beforehand rather than afterwards when enough fraud has happened and then we recognize that, oh, it is fraud. That's not useful. And so the new problem is, can we count such that recent emerging counts are also identified? So these are not quite so heavy hitters, but these are recent. And in particular, we want the estimate of recent count to be better than the older ones. Why do we want to be better than older ones? Because we are given the limited budget, and these count when sketches algorithm are optimal, so you cannot beat them all the time. But then what you want is, can I have a better algorithm if for recent counts, and I am little bit okay if I to tolerate some error on the older counts. So it's like our memory, we keep forgetting the old things as we keep seeing new patterns. So this is ideally what we want. And what people have done, this is the work by Smola, Ahmed, and I don't know how to pronounce this. So this was from Yahoo and Google. So the idea is, so memory and there is a trade-off between memory and accuracy. So this count when sketches, the more memory you give, the more accurate they are. So the idea is, what you can do is, for recent intervals, you allocate more memory. So you allocate a count sketch for a bigger size for recent time intervals and smaller size for old time intervals. So if you are given a limited memory budget, then you allocate in this fashion, and because this time instance has more memory, it will be more accurate because of the memory accuracy trade-off. That's how these things work. So there are some immediate problems with this, that you are keeping track of every time. So for every time you have this sketch. So that's like big O of t. And note, you have to do this on a streaming fashion. So as t increments, you have to shrink few intervals, shrink few sketches. So you can do it on the fly. There is a smart observation that you can add one half of the count sketch on the other half and just take mod 2 of your hash function. But you can shrink them on the fly, but it requires some work. So there is a shrinking overhead. In particular, there is actually more trouble with this. So what do I mean by discontinuity here is, suppose the time t is empty. You don't observe, like for example, it is midnight and there are no activity. But your time has progressed from t to t plus 1. So you still need to shrink the sketch of time t. Now if you are shrinking, you are just doubling its error. So you are doubling the error and you haven't observed anything. So that there is some sort of discontinuity there. As we have seen that we need a lot of memory, there is a shrinking overhead, and in fact there is no flexibility, because these algorithms were meant to keep like what is known as the dyadic interval. So this is 2, so this is 2, this is 4, then 8, and so on and so forth. And you don't have flexibility over that, because that's how this algorithm works, because you want to do everything on the streaming fashion. Alright, so how do we fix them? So let's take a slight detour and look at how we do noise reduction in Dolby systems. So what happens is, when you are recording a sound in Dolby, there is something called a tape hiss, which is high frequency. And therefore, it actually messes up with the high frequency signals in the recording. So the work around this is, while recording, you attenuate you increase the amplitude of these high frequency sound by artificially inflating, and then you record it. So then everything messes up, the tape hiss messes with the recorded sound, and when you are playing back, you just apply a reverse transformation which shrinks all the high frequency amplitude of the high frequency signal, and that also shrinks the tape hiss. So effectively the noise gets sharply attenuated. So we are going to exploit similar idea. So here is what we have. We have a sketching algorithm which is very accurate for heavy hitters, and it has a lot of distortion for not so heavy hitters. So what we'll do is, we'll artificially inflate recent counts and add them to the sketch, just like pre-emphasis. And when after estimation, during the estimation, we'll deflate it by the same amount. And the reason why it will work is because the noise will attenuate it sharp. So okay, so what we'll need is, we'll need a monotonically increasing sequence, call it alpha t for now, and we'll treat every pair, item, comma, time combination as a different item. So the same item at different time intervals is, you can think of it as a different item. You add it to the sketch after doing this pre-emphasis, that is artificially inflating them, and while querying, you get the estimate and you deflate it by the amount you have inflated. So one thing is clear, if there is no collision, then this is exact, because you multiply by something and you divide by the same amount. So if there is no collision, you are estimating exactly. Now what happens when there is collision? So let's look at this counter, and let's say, okay, this is not visible, but let's say this is item I at time t, and this is item j at time t prime, where t is greater than t prime. So this is recent and this is old. Let's say both of them come to the same bucket, or the same hash bin. Now, due to this emphasis, what is in the bucket is alpha t c, whatever is this, and alpha t prime c j t prime. Now we know that if t is greater than t prime, then alpha t is greater than alpha t prime, because that's how we designed this monotonic sequence. Now let's look at what is the error in estimating this CJT. So remember, we take the counter and deflate it by the amount we have inflated. So what we get is the original count plus this noise. If we wouldn't have done pre-emphasis and de-emphasis, then this noise would just be CIT prime. But because of this ratio, where alpha t prime is greater than alpha t is greater than alpha t prime, this will be less than 1. And so we are getting better errors than Cartman sketch. And opposite happens for older intervals. So we are trading off errors slightly smartly, in which we are ensuring that we have less error for recent time intervals and more error for older time intervals. And there are, like, we haven't changed the procedure much. So look at so we have the Countman sketch algorithm. All we are doing it, before adding a count, we are doing an artificially inflating some of them, and when estimating, we are deflating some of them. We have no overhead, there is no discontinuity, because if time t is empty, then we are not adding anything to the sketch. There is no collision, no extra errors. We are order locked in memory, that needs some analysis, so you have to analyze how Countman sketch work, and then you take a union bound for basically for all. So it works, so it's log into n. Now we have n into t items, so it's still log n into t, so it's still log t. And there is no shrinking overhead, because we are just using one sketch. We never need to shrink anything. Like in Hokusai, we have to shrink the size of the sketch on the fly, which requires a lot of work. And in fact, we have a choice how we can use this any monotonic sequence work, and therefore we have a choice of what we want for alpha t. So we have more control over what the error trade-off we want. You can prove some theoretical guarantees that you can show that the error estimate is actually adaptive in time. That is, this error bound shrinks as time increases. Anyway, this is the accuracy. So we use the AOL and the Criteo query logs, and we count the number of turns over time. And so this is the time axis, and this is recent and this is old. The black ones are Hokusai, the idea where you keep shrinking as you go on. There are these plots which are adaptive Countman sketch and adaptive with exponential decay, that is alpha t is chosen to be exponential to the power t. And you can also choose linear, you can choose 8 into t, both are monotonic. And that shows you how you trade off the errors. And the red dotted one is vanilla Countman sketch. So if you just use Countman sketch, and this is the time thing. So you can so this is absolute error, and this is the standard deviation of those errors. So what you can see clearly is that Hokusai and the adaptive variants have the adaptive nature, that is, they are very accurate for recent time, and as the time goes off, they become worse. But you can see that for the same amount of memory, that is 2 to the power 18 in this case, the new scheme with pre-emphasis and de-emphasis is significantly more accurate than the ones with Hokusai. Because the lower is better, this is absolute error, and this is standard deviation, again lower is better, and you can see that this is always better. So that is, in fact, it's a lot better. It's not just this is like 500 versus 1500, this is a lot better. So that's one thing, and you can also look at the scalability. So this is the size of the sketch size that you give, and then you summarize the whole data set using that sketch, and you see how much time it takes to summarize. And CMS is of course very fast, it's known, and if you do linear updates, it's also very fast. Exponential is slightly slow, but it's again, it scales, it doesn't get worse as you increase the memory. Whereas if you look at Hokusai, it just goes worse, worse, and very worse. And the reason is again, because as time increase, you basically for every time t, you are doing logarithmic many sketches and you are shrinking them. So that creates a lot of overhead. So this is quite costly. So yeah, that is all I wanted to tell. And so basically online environment bring interesting big data challenges. Learning with counts is a scalable approach for many applications. Randomization is not bad at all. And the idea of pre-emphasis and de-emphasis can be applied to sketches, and we get some more control in how we distribute errors. So yeah, that would be all. Thank you very much.
Very nice talk. I particularly enjoyed because I'm from EE. I see there's a rage you're doing kind of EE and CS. I take it's like you cite the paper from EE 1960, like 50 years ago. Back then, people studied signal, right? That's signal is the EE concept. And now people talk about data science, big data. Essentially, each signal sample is a data point, right? So since I don't work in this area, I try to get to the gist of the. So I believe it's not simply just convert the sample into data, then that's it. So we just take all the EE knowledge that we work, right? What is the new? What is the computer science twist there? Like advancement of that body of knowledge.
So, computer science, like I think in big data world, like computer science is exploiting parallelism, like how do we exploit parallel algorithms, how do you want to do communication, low memory. So for example, I showed you count min sketches, which was discovered in computer science with a very different motive. They wanted to look at like a limited memory, and then they want to count. Whereas a very similar problem was solved in E, and like as compressed sensing, and they want to look at signal measurements because they want to transmit. So now it's actually the gap is closing because both of the world is now talking in terms of communication complexity. So if you look at these sketching literature, they will say, oh, what is the communication lower bound, and then that is where both the ideas are now becoming converging. But yeah, that's
so my impression, little impression, maybe impression
sure.
is the E. I'm actually a CE, computer engineer, so I'm not maybe wrong with EE too. So the EE people are more analytical. They don't care about memory size, as you mentioned, right? They don't have heuristics. They make some simplifying assumption about channel or signal, and then this is a statistical model. The same signal will follow. They will provide analytic solution, right? And throughout your talk, I heard a lot of heuristics. You see, for example, most of recent data matters more than old data. So it seems like the more heuristics into the framework, and as a consequence is would your results compared to the E results will be more limited in providing analytic answer.
Oh, so
closed form analytic.
Okay, so I didn't put math in the talk. So count min sketch, as I mentioned, that is 1-to-1 in compressed sensing. And even with count min sketch, you require only k log k measurements to get top k, which is also the lower bound in compressed sensing. So the kind of idea, so what is, so again, where was all these discovered? These were again discovered as a heuristic. So I think the people, if you look at who the discoverer of count min sketch are, they were working at Google, and then they were solving this problem, and they realized that this heuristic works very well. And then they come with a theory. And later people realize, oh, this theory is near optimal for what is known as compressed sensing. So you're right.
We actually prove the heuristic as
yeah.
good.
So even with this pre-emphasis and de-emphasis, what you can do is this: you can actually ask questions. What is this alpha t? So you say that, okay, I want to preserve. So you can formalize now that you want to preserve every count compared to count min sketch with at most gamma distortion. So I don't want more than gamma distortion. But I also want that the time instance from 0 to, let's say, t should be better than count message. Then you can write down a simultaneous set of equation and you can solve it. So yes, it is heuristic and it comes from practitioners, because again you see that there was a paper written by Google folks which says that you want to shrink it because it's observed that if you are better on recent count, then you basically do better. But then you can start formalizing things, and I think that is where the CS thing is like it's mostly like coming from practice, what people are doing and what worked, and then people start formalizing. And that is when most theory come in, and actually they borrow ideas, and it's hard to tell these days who is CS and who is EE, because with data science everything is now, just I mean privacy, everybody's doing privacy. It's hard to say it's easy EE or CS, so those things are coming. And again,
so yeah, my comment here is just that we probably should stop labeling everything as belonging to CS or EE. I mean EE is just an older discipline than CS. There was no computer when people were playing with circuits. So electrical engineering is much older discipline. And when people started, looking at communication, they wondered like information theory, and so the whole information theory discipline was grown out of electrical engineering. People who were playing with electrical circuits and whatnot and trying to transmit signals as well. So of course then sort of many of the development in information theory happens to come from EE, and then to science, it's a much younger discipline. There's no computer to speak of until 70 years ago. So, but it seems like today it's just very blurred. People in CS do information theory. I think Anshu is one of those people as well.
yeah, and just to add one more thing, these days like a lot of people are having complaints with computer scientists that they are stealing everything. But no, I've heard it at a lot of conferences. Like I was at some conference and there was a behavioral scientist and he was not very happy with what computer scientists are doing. But I mean I totally see that part, but the thing that we should observe is like with these computers, now we can observe much more than what we could have observed with our mind. And that is why CS people are like now seeing the problem before others. And in fact, Dan was mentioning me a quote that one of the good quote about computer scientists that he heard was that computer scientists pick low-hanging fruits where people don't see the tree. So I mean that is what is happening. So it's said that most of the people, and you will also find it written somewhere, that Google people says 7 to 8 years ahead of what others are thinking. It's because they are seeing the problems, which probably we will see later. And so they know what the problems are, and so they are developing heuristic theory, whatever, and so that is what is happening. So practitioners have some advantage here.
So in the graph you showed, so you ran the CMS algorithm with same parameters as your algorithm?
So basically both of them are given the same memory. So same D, the depth is same and the width is same. And with Hokusai you just run the shrinking part, and this you just do pre-emphasis.
So the baseline, which is the CMS one, so what is the core advantage of using the
So you see better errors on recent time, right? You see much accurate on recent time. So you cannot beat CMS all the time, because then you would have broken probably the lower bound of I don't know if it's proven to be lower bound, but I think K log K is considered to be lower bound. So if you are always accurate than CMS, maybe you are you found something much more than it will be a lot more. So yeah, the last slides, yeah.
Okay, let's thank the speaker. And we don't have a colloquium talk next week because of Thanksgiving, but the week after that, Eugene.
Maybe.